Alright, we're going to try to get page 1 done here. So we're looking at the first one. How many distinct monochlorinated products, including stereoisomers, can result when 2-methyl-2-propane or 2-methyl-propane is subjected to free radical halogenation? And we're going to do it with chlorine. Alright, so these end locations each have 3 hydrogens. So does this one. And any one of those any of those hydrogens can be replaced, and we get just a single product because that has no stereocenters. Or we can replace that middle location and get a second product. So yeah, there's only 2 monochlorinated products. Alright. We're going to follow it up with this next one because we got butane. When it's subjected to free radical chlorination, how many distinct monochlorinated products are possible and how many contain asymmetrical carbons? Alright, so standard butane, just 4 in a row. And if we react those with chlorine, we could replace one of these 6 on the end. Give 1 chlorobutane. Or we can replace one of these 2 in the middle and get 2 chlorobutane. And a nice little rule of thumb is it is going to be 2 distinct actually I'm going to change that because it's going to be more than 2, because that location has 2 hydrogens, so it's a CH2, and whenever we actually halogenate a CH2, we likely create a stereoisomer. In this case we did. So there's 2 of these. There's an R and an S. And so there's 3 distinct monochlorinated products, and 2 of those create asymmetrical carbons. Alright, number 3. Provide the structure and the name of the major product when we react 3-methyl-heptane. 2, 3, 4, 5, 6, 7. 1, 2, 3. Methyl-heptane with bromine. Oh, and light. Alright, so being that it's bromine, we're going to actually end up putting that on the most substituted location, so we only get 1 product in this case. 1 major product. 1,600 times more likely than almost any of those other locations. So that is our structure. It is specifically R here, but since we create a free radical in the propagation step, this is going to be an R and an S. And it wants the name, so this is going to be 3-bromo, 3-methyl, heptane. No rearrangements, none of that silliness, not for this one. Alright, number 4, provide the most likely propagation step for the, I must have bumped my key, for the most likely propagation step of propane. I'm not sure what I'm doing there. Alright, so propane, CH3, CH2, CH3, and we're reacting that with chlorine. And most likely product would be 2-chloro. Now that's the complete step, but the propagation step that they're going to want us to have here, we're going to need to show that propane, does indeed get attacked by a chlorine radical. The chlorine radical makes the HCl at the expense of the propane. where it becomes a radical. And then in my next step, a chlorine gets attacked by that radical, to make our substituted product and another chlorine radical. So our propagation steps show making of a radical, making of a radical from a radical, and then we take that radical we made and destroy it and remake the original radical. Alright, number 5. Alright, I have an alkane and I need to substitute stuff on it. So I know my very first step, I'm just going to take something like bromine or chlorine and substitute a bromine or chlorine onto that. And I want to do alkenes, so I'm going to do an elimination. Probably do this with just some OH and some heat. But you know what? Just to make sure we don't get any substitution products, let's go with a bulky base. That will give us a simple alkene. Now I'd like to repeat this. So I kind of want to do something like this, where I put the bromine in that position adjacent to the double bond. And if you remember, we did that with MBS. And then we can do a follow-up elimination. Now this one we probably can do with just OH, because it's going to favor the elimination. But I'm going to do it with the same base again as we did in that second step, and kind of force the situation. Alright, number 6, starting with cyclohexane. How are you going to create 3-methylhexene? Alright. Turns out this is going to be very similar to what we have up above with Br and light must be used to get a substituted alkane. And then we'll do that same thing as we did there to make an alkene. Alright, I'm going to need to erase this, it's in my way. Alright, now this next step is combining our previous idea. We're going to use that MBS again. Put a bromine there. But now instead of eliminating it, we're going to do a Grignard reaction. So we have a methyl magnesium bromide. Guess we could do that with CH3 with lithium. Actually, what I'm going to do is do both. So with the magnesium bromide, we want this to be down here ether. If we did it with the lithium, we can just say down here hexanes. But either way, we'll do a substitution of that alkene, or that bromine, with a single methyl, giving us the final product. Now, this step right here might be in a chapter that is skipped the semester you took it, this class. So that is something we'll be adding in Orgo 2. And if that's the case, if you haven't seen an organometallic chapter yet, I'd probably stop right there on this particular problem.